All right, we still have the clicky mic because I forgot to bring the good mic today. But not the next lecture, but the lecture after that I should have it, because the next lecture is just during lab. So, starting off, new chapter, periodic properties of the elements. So picking up where we left off, sort of with chapter 8. Chapter 8, remember we were learning about quantum mechanics. We learned about our principal quantum number, n, 1, 2, 3, ... We also had L, our angular momentum, our ang-mom quantum number that goes from 0 to n minus 1. We had M sub L, which is our magnetic quantum number, which goes from negative L to positive L, includes 0. We also had M sub S, our spin quantum number that was plus 1/2, minus 1/2. We're going to be doing some stuff with these numbers this time. So we're adding some concepts to these. Primarily, we're going to be dealing with our principal quantum number and our angular momentum quantum number. Magnetic and spin will both come up as well. For magnetic, we're not really going to use it quite as much. We're just going to use the number of numbers that we have for magnetic. And for spin, it's just plus or minus 1/2. So we're just going to be using those as up and down. I have this also in the last set of slides written out at least once. Okay, so the modern periodic table, one that we have in the class on our yellow sheet, anywhere else that you look it up, is thanks to Dmitry Mendeleev. It used to be that the periodic table numbers, elements, were just laid out in lines. They just had a set number of them. They didn't have all of them, and they sort of were filling them in as they went. And Mendeleev, when he ordered them by atomic mass, saw a repeating pattern of properties, and that led to us laying it out the way that we currently have it. So Dmitry Mendeleev proposed the periodic law. When the elements are arranged in order of increasing atomic mass, certain properties recur periodically. Sometimes they do not go in order. So tellurium and iodine are not in order. Tellurium has a higher atomic mass than iodine. And so rather than putting them in order for that, for atomic mass, he put them in based on their properties. Mendeleev also made some predictions about elements based on things that he knew probably existed but they hadn't discovered yet. Gallium and germanium, I don't think is particularly important, but you can look at that if you're interested in why that is. So Mendeleev's periodic law, because it's a law we can predict what the properties of an element will be based on its position on the table. Not so much anymore because we've filled out all 7 rows. Theoretically, there are some extra rows past that, but we haven't discovered those elements yet. However, his periodic law doesn't explain why that pattern exists, why the periodic table trends are the way they are. We can use quantum mechanics and some extra information to sort of explain why those properties are the way they are. So the electrons in atoms exist within orbitals, s, p, d, f orbitals. Spheres, peanuts, double dumbbell, and the weird ones, the f orbitals. So electrons exist in these shapes. And remember that these shapes, the sphere, the peanut, the double dumbbell, etc., these are where they're likely to be found. Electrons are likely to be found in a shape that's a sphere, the dumbbell, the double dumbbell, and the really weird ones with the f orbitals. We can describe where the electrons are, which of these have electrons, with an electron configuration. So for our electron configuration, we have our n, our principal quantum number, paired with an orbital, either s, p, d, or f. And we're using the letters instead of L. And then we can write the number of electrons that are in that orbital in the upper right-hand position on the letter. So for hydrogen in the first row, it only has access to the lowest energy orbitals. So starting with n equals 1, the only orbital, the only subshell that we have there is s, and 1s with 1 electron in it, because hydrogen has 1 electron. So the 1 electron can go into the s orbital. If you do calculations with Schrodinger's equation, it will show that the hydrogen's 1 electron occupies the lowest energy orbital in the atom, which is going to be the 1s. For multi-electron atoms, you can't solve it because there's a lot of extra stuff that goes on. Some of those things being electron spin and energy splitting for sublevels. So the sublevels being these s, p, d, and f subshells. Subshells are sublevels. We can also do orbital diagrams. This is essentially a visual electron configuration. So far, most of this should be review from Chem 20. So this is a visual electron configuration. We call it an orbital diagram, and so we're going to use boxes. I'm usually lazy, and so I'm just going to put a line at the bottom rather than drawing out the whole box. I think it conveys the same amount of information. So this little line, this is our box for the 1s orbital. We've got 1 electron in it because it's hydrogen. We only have 1 electron. And usually I put in the electrons with an up arrow first. Our options are up and down. And I draw them with half arrows. You could draw them with full arrows, I guess, if you wanted to. Probably doesn't make a difference. And this is where the spin quantum number comes in, that m sub s. So it can have values of plus 1/2, or the down arrow would be minus 1/2. So the up spin and the down spin are represented by an up arrow and a down arrow. If you draw it in with the down arrow instead of the up arrow, that's also accurate. Half of the atoms in a group of hydrogen atoms, half of them are going to be spin up and half are going to be spin down. It's about evenly split. Okay, our first rule with electron configurations and orbital diagrams is the Pauli exclusion principle. Under the Pauli exclusion principle, no 2 electrons in an atom may have the same 4 quantum numbers. 2 electrons in the same orbital, the same shape within a family, have 3 identical quantum numbers. So 2 electrons in 1s will have n equals 1, because that's the number that goes in front. S corresponds to L equals 0, which is our only L option, our angular momentum quantum number option. And then it's going to have m sub L also of 0. So both of the electrons are going to have those same 3 quantum numbers. And then the 4th quantum number has to be different. So for 1, the m sub s is going to be plus half. or the other, m sub s is going to be what? Minus a half. It has to be the other option. A lot of words to say that each orbital can have a maximum of 2 electrons and they have to have opposing spin. So for example, if we had helium, which is probably coming up soon, our 2 electrons in the 1s, one would have upspin, the other one would have downspin. So you can't have 2 up arrows, you can't have 2 down arrows, it has to be 1 up, 1 down. And we'll draw some that are wrong. So the maximum number of electrons that we can have in a sublevel in S, P, D, or F is twice the number of orbitals. So S has 1 orbital, it can hold 2 electrons. P has 3 orbitals, it can hold 6 electrons. D has 5 orbitals, it can hold 10 electrons. And F has 7 orbitals, it can hold 14 electrons. If we look at helium, here's that example that I showed us earlier. Helium has 2 electrons. They can both fit into the 1s orbital. The smallest little sphere can hold 2 electrons because it's 1 orbital. 1 orbital, 2 electrons, and they go on with up and down spin. If we have multiple sublevels, for hydrogen, the orbital energy depends only on the n number. And any of the orbitals with the same energy we call degenerate. Degenerate just means the same energy, which I think is funny. It's not the degenerate that we normally think of. For multi-electron atoms, the energy of the sublevels are split. So 2s is different from 2p, for example. Different energy from 2p. And this is caused by a couple of things: charge interaction, shielding, and penetration. Generally, the lower the value of L within a principal level, the lower the energy of the orbital. So generally, S is the lowest energy, then P, then D, then F for any n number. When you change the n number, things can shift around a little bit. But conveniently, they fill up in the order of their number. L equals 0, L equals 1, L equals 2, and L equals 3. So S, P, D, F, they fill up in that order, where they increase in energy in that order. Any questions or confusion so far? Cool. To help us out with explaining the why for some of this, we're learning some extra terms. So this is new stuff for Chem 1, stuff you wouldn't have talked about probably in Chem 20. Coulomb's law. This is the same one that you would probably use if you took a physics class and you did electricity, or you did charged particles. Coulomb's law says that the potential energy, the energy of 2 charged particles, like electrons, like proton and an electron, depends on their charge. Charge is Q1 and Q2. and on their separation. So the distance between the particles and our energy there. And this first term, we've pulled out everything in front that is a constant, or that's constant at least for us. So for like charges, the energy is going to be positive. The charges are going to repel. For opposite charges, E is negative. The charges attract. So we're going to see negative energy between proton and an electron. Negative energy is stabilizing or stable. The strength of the interaction is going to increase as the size of the charges increase. The potential energy will also increase as the particles get closer together. So this is like if you've got two magnets and you bring them closer together. When they're really far apart, there's basically no interaction. When you bring them closer together, suddenly they want to jump towards each other. That increases the closer you get until they're touching. So the energy, how strongly they're pulling each other, increases as they get closer together. We're going to use Coulomb's law to explain some of these phenomena with electron configuration energy levels. In a multi-electron atom, each of the electrons is going to experience the attraction of the nucleus and the repulsion of the other electrons in the atom. Especially the core electrons. So remember that we can still think of things as our Bohr model of the electron. Let me do some different colors in here. This would have 3 protons. So this is lithium. So these red dots here in the middle, that's our nucleus. We've got 3 protons. Protons have a positive charge. We also have 2 electrons in our n equals 1. So this electron here on the outside is going to experience the pull interaction with these 3 protons on the inside. It's also going to experience repulsion with the 2 electrons. I'm going to change this one to green. So it experiences a pull with 3 protons and push or a repulsion with 2 electrons. So it's also interacting with the 2 electrons that are on the inside. So it's got 3 pull, it's got 2 push. What's its overall pull? Assuming that everything is the same, assuming that pull and push are equal.
Neutral.
3 pull, 2 push.
Oh, sorry. The 1 positive.
Yeah, so it's going to have a 1 positive force. So if we draw this as an arrow, let's make that 3, and it's going to experience 2 push. So it gets a net 1 pull. Does that make sense? Hopefully makes sense. This is all explained in later slides. I don't know why I'm explaining it all right here. Essentially, this is what we're talking about with shielding and effective nuclear charge. So these 2 electrons on the inside reduce the attraction to the nucleus. So these 2 electrons on the inner shell basically cancel out 2 of these protons. So core electrons cancel, sort of cancel out protons. And so the effective nuclear charge is the protons minus the core electrons. And I think this all comes up in later slides. Summary slide may be there for you. So that's one of our effects. There's also penetration, which has to do with how the orbitals overlap. And we'll see some visual of this. So the better an outer electron is at getting inside of the electron cloud of the inner electrons, the more attraction it will have for the nucleus. So remember, for our 1s sphere, it's just a solid sphere. When we go to 2s, it's going to have see if I can draw this correctly. It's going to be more of a donut. I need to redraw this outer sphere. This is like a bad example of a cross section. So there's going to be a zone where there's no electron density, which is that empty donut part. And then for our 3s, we get 2 of these, and I'm not going to attempt to draw that. You can go back and look at the chapter 8 slides. It shows that. We might also see some pictures of that. So for our 1s, we've got the sphere. For our 2s, we've got this little donut that's going to be inside of that 1s. That's what we're talking about when we're talking about this penetration. It's got overlap with the 1s sphere. And because it's got overlap with the 1s, that means the electrons can effectively be inside of the 1s. That's the penetration part. But there's also this density that's outside, and so that's not going to get inside that 1s, so it's going to experience the shielding. So for this section, this is shielded by 1s electrons. This inside part may be inside the 1s, so it's unshielded, or less shielded at least. So it's shielded, sort of. If we were to overlay on top of this our p orbitals, I'm just going to do that briefly because it's going to look super confusing. If we've got a p orbital and we overlap that with our 1s, we've got very little overlap between our p and our 1s. So the amount of time that's spent inside of the 1s, or the amount of density that's inside the 1s, is much smaller compared to our 2s, which has the whole donut ring in there. So less penetration. So for shielding, an electron that's outside experiences a net charge of +1. If it's inside of that energy field, then it experiences the full 3+ charge. So this is what I was talking about on the previous slide with my little diagram. It's inside of these 2 electrons, and so it's not shielded. These electrons aren't blocking or canceling out the positive charge from our protons. Okay, a graphical view of our spatial distribution. So we're looking at our total radial probability This is the better one that we talked about in chapter 8. So our 1s is going to have most of its probability density really close to the electron. It tapers off the further up you go. If you look at our 2p orbital, it's got some overlap here. Right, so all of this red line region, it's got some overlap there. But if we look at our 2s, because it's the same shape as 1s, it's got this little donut part in here where it's inside of the 1s. And so this whole area is not shielded, versus for 2p, it's got this little cutout. It's not quite as good as the 2s. Effectively, all that this means is that 2s is lower in energy than 2p, which we knew from, where is it? This slide. S is lower in energy than P. So that general rule of thumb still applies. We're just showing you why that is here. So because of that penetration, the way that the different shapes overlap, the sublevels of each principal level are not degenerate. They don't have the same energy because of the way that the shapes overlap with each other. In the fourth and the fifth principal levels, the effects of those overlap effects become so important that the 4s orbital lies lower in energy than the 3d orbitals. I'll show you how we can come up with that in a different way, or how we can remember that in a different way. Energy separation between orbitals becomes smaller beyond 4s, so the energy levels get closer together. Here is the general energy ordering for the orbitals in multi-electron atoms. We've got them grouped by s, p, and d. So our first column is s, second column is p, third column is d. This is just so we can keep our s, p, and d's straight. And then their energy is shown on the y-axis. So 1s is the lowest, 2s is next, then 2p, then 3s, then 3p, and you would expect 3d to come next, but 4s comes first. So 3p, 4s, 3d, and you can see these get really close together. So 4p, 5s, 4d, and they get closer the further you go up. You do not have to memorize this. You can. You don't have to, but again, you can. There's another way that we can come up with the energy filling order. Generally, for our orbital filling, we go with the Aufbau principle. Aufbau, if I'm remembering correctly, is basically just German for construction. So we start at the bottom energy levels. If you build a house, you need to put in the foundation before you can put in all of the other layers above it. So the electrons are going to occupy orbitals that minimize the energy of the electrons. Lower energy orbitals fill before higher energy orbitals. Orbitals in the same sublevel have the same energy. So we have labels for our individual orbitals within our p sublevel. They're x, y, and z. I don't know, I did them in the wrong order. So 2px, 2pz, 2py are all the same energy because they're within the same p sublevel. So these are going to stick together, and that's like what we see with this diagram. Our 2p's are all the same, our 3p's are all the same, our 3d's are all the same. So for those, the energy level is the same. Because of our Pauli exclusion principle, orbitals can hold no more than 2 electrons each, and the spins have to be opposite. to have plus 1/2 and minus 1/2 quantum numbers so that they don't have 4 duplicate quantum numbers. And then our third rule, Aufbau principle, is sort of a rule. Our second actual rule is Hund's rule. So when we're filling degenerate orbitals, degenerate meaning they have the same energy level, like 2px, 2py, 2pz, the electrons fill in singly first with parallel spins. So if we were doing an energy diagram or an orbital diagram and we're filling in our 2p, let's say that we've got 3 electrons to put in, we would fill them in up, up, up. So parallel spin, in this case, all with up spin. Not like this. So we wouldn't pair them up first. They would all get in sync with upspin. Once they all have one with upspin, then we can start filling in the downspin after that. Questions about our Pauli exclusion principle? 2 orbitals, 2 electrons per orbital, 1 up, 1 down. Aufbau principle, we're filling in lowest energy to highest energy. Hund's rule, we fill our electrons in singly with parallel spin first. Questions about either of those, any of those? Cool. There's also this analogy, Mrs. K's Chemistry Land. There's the Quantum Hotel in Chemistry Land where you can stay. In the Quantum Hotel, the first floor has 1 room, the second floor has 2 rooms, the third floor has 3 rooms, etc. So it's sort of this like weird upside down triangle shaped hotel. And it would look something like this. So we've got 1 room on the first floor. On the second floor, we've got an S room and a P room, then S, P, and D. And we're using the American floor numbering system, not the British. So in each of these rooms, the S rooms, S has 1 bed, and they're not big beds. They're like doubles or queens. They're not king-size beds. You can't like squeeze 3 people into 1 bed. So it has 1 bed. The maximum number of people you can put in 1 bed is 2 people in this hotel. In our P has 3 beds. D has 5 beds. Let's say that you and 2 of your friends are going to the Quantum Hotel because you're an electron in this situation. If you're 3 people in a 3-bed room at a hotel, how are you probably all splitting up the beds? Are all 3 of you cramming into 1 bed? No, that'd be crazy, right? There's 3 beds, there's 3 people. Put 1 person in each bed. Everyone gets their own bed, and then you don't have to touch another person in your sleep on accident, or have somebody be uncomfortably warm next to you, because that seems to always happen. So 3 people in a 3-bed room. Probably also, everyone is sleeping the same direction. They're probably all sleeping with your heads towards the wall. You're not a maniac sleeping with your feet towards the wall and your head sticking out in the middle of the room. If you do that, that's fine. It's whatever you want. If you have 4 people, then what happens? 4 people in 3 beds? Somebody's got to double up. And because we're apparently not mature in this situation, I guess. Maybe we're a little weird. Maybe it's like a camp situation and we've got basic beds and we're sleeping in a sleeping bag. We're going head foot. So you get to smell somebody else's stinky feet and they get to smell yours. And if you have 5 people, then you add another person to the second bed. If you have 6 people, you add another person to the third bed. And if you've got 7 people, go to another room. We're not fitting in 7 people into this room. They don't have, they can't bring in an extra mattress like they can at hotels. Not at the Quantum Hotel. Okay, unless stated otherwise, electron configurations refer to the ground state, the lowest energy configuration, which is great for us. The number of electrons in a neutral atom equals its atomic number. So if we look at phosphorus, phosphorus on the periodic table has 15 protons. That means that it also has 15 electrons. Electrons with parallel spin have correlated motion that minimizes their mutual repulsion. They're all in sync. They're all doing the dance moves at the same time, and it's very aesthetically pleasing. Our S sublevel has 1 orbital, our P sublevel has 3 orbitals, D has 5, F has 7, so they can hold 2, 6, 10, 14 electrons respectively. There are other ways that we can remember these things that I'll point out when we get there. Okay, so electron configurations can be really long. For example, for krypton with 36 electrons, this is the full electron configuration, and it's kind of annoying to have to write out all of this. Not to mention you also have to remember how the energy levels fill up. So this would read 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. We could write that much shorter with this shortcut. We love shortcuts. So a shorthand way is to use the symbol of the previous noble gas. Noble gas 1 row up. And that represents all of the inner electrons. So for rubidium, on the periodic table, it's got 37 electrons. Rubidium. If we look at the previous noble gas is always behind you, so that's going to be krypton, which has 36 electrons. So we're going to write Kr in brackets, and that represents everything up through krypton. So it represents 36 electrons. We have rubidium, so we have 37 electrons, so we have 1 more, and we just add that 1 more electron to the next energy level. And the next orbital that we would fill up is the 5s. We've got 1 electron, so it's 5s1. More electron configurations for you to look at while I go close the door. All right, let's write an orbital diagram for AR and determine the number of unpaired electrons. So argon has how many protons? 18. So how many electrons does argon have? Also 18. It's neutral, so it's the same number of protons as electrons. 18 electrons. We're going to write the full orbital diagram for argon. We also need to do an electron configuration for argon. Usually we do an electron configuration before, and then we do the orbital diagram afterwards. So filling up our energy levels, our lowest energy orbital is our 1s. How many 1s orbitals do we have? How many shapes do we have? It's just the one sphere, so we can put 2 electrons in there. That's what we were saying with 2. So if we have 18 electrons and we put 2 of them into the 1s, now we've got 16 electrons to place. In our n equals 1, the only sublevel, the only shape family that we have is s. So we have to now go up to n equals 2. So we go to 2, we have an s. This s also just has 2 that can fit into it. So now we've got 14 electrons left. What comes after 2s? 2p. We get 2p. And how many shapes do we have in p? 3 shapes, 2 electrons each, 6 electrons. So minus 6 electrons. We've got 8 electrons left after we do that. Do we have any other letters in n equals 2? So for n equals 2, the thing that determines what shapes we have is L. L can be 0. It can go up to n minus 1. So 0 and 1, or S and P. So we don't have any more sublevels or subshells. So that means that we move up to 3. So n equals 3. We start over with S. We can fit 2 into that. We subtract 2 electrons. Now we've got 6 electrons left. After S comes P. We can put all 6 of our electrons in there, and now all of our electrons are placed. So that would be our electron configuration. And then we can follow along with our electron configuration to make the orbital diagram. So we're taking the 1s and we're making one box for it, or in my case, one underline. We put 2 electrons in. How do we put the electrons in? One up, one down. And then next up is 2s. S has one shape in it. So 2s gets one box. This one's also up and down. And then next is 2p, and p has 3 orbitals in it. We're putting in 6 electrons. It's completely full. So we're putting in up, 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 down, down, down. If you want to, while you're filling them out, if you know that they're all full, you can just fill them up, down, up, down, up, down. That's fine with me. It'll save a little bit of time. After our 2p, we move on to our 3s. Since it's an S, it gets one box. It's only got one shape in it. It's only got one M sub L in it. We fill that up. It's up and down. Then we've got 3p. It's a P subshell, and so it also has 3 shapes. We fill them in up, down, up, down, up, down, because we know that they're all full. How many unpaired electrons do we have? 0 unpaired electrons. They're all matched by another electron or paired up with another electron. For main group elements, things that are not in that middle block from scandium to zinc and down, for our main groups, everything that's not there, the valence electrons are the ones that are in the outermost principal energy level, the highest n number. So those are our valence electrons. Valence just means outside. So this is our outermost shell of electrons. The group number, groups are columns on our periodic table, corresponds to the number of valence electrons. And we're talking about the A designation. So 1A, 2A, 3A, etc. This corresponds to the number of valence electrons. So the number within the main group, 1, 2, skip a few. all of our transition metals. Then we're on the aluminum group, that's 3. Then 4, 5, 6, 7, 8. Noble gases are 8. So that's the number of valence electrons that we have. So aluminum in 3A has 3 valence electrons. Electrons in the lower energy levels, anything beneath our highest N number, is our core electrons. And the number of valence electrons is crucial for understanding the way that an atom behaves, which is why we're talking about them. We'll also be using the idea of valence electrons in the next chapter to do more fun stuff. So looking at our periodic table, we've cut out our transition metals. Our transition metals would go there, so we're just looking at the main group elements. They've got 1, 2, 3, 4, etc. valence electrons. And notice that the row that we're in corresponds to our highest N number. So 1, we're filling up our 1s. In 2, we're filling up our 2s and our 2p. In n equals 3, we're filling up our 3s and our 3p. So the row number corresponds to the N number that we're in. Questions so far? If you want a different or more in-depth treatment, me talking about this, I talk about it in different ways with different slides in my Chem 20. So you can go find the chapter 7. I think it's in the middle of chapter 7. So probably parts 3 and 4 from this semester. Okay, we want to write an electron configuration for phosphorus and identify the valence electrons and core electrons. So first thing we need to do is find phosphorus. Phosphorus is P. We find phosphorus in row 3, and it's over on the right side of the periodic table. So it has 15 in the upper right corner. Phosphorus has 15 electrons. Our first energy level that we fill up, N equals 1. And in N equals 1, we just have our S subshell. We've got one shape in there. We can put 2 electrons in each shape, so 1s2 is full. Then we move on. The next N level, the next principal quantum number level, is N equals 2. We also have an S in there. It can also take 2 electrons. So minus 2 electrons, and we've got, after that, 11 electrons left. N equals 2 also has a P subshell. P has 3 shapes. Each of those shapes can hold 2 electrons, so we can fit 6 electrons. So minus another 6 electrons, we're down to 5 electrons. P is the highest letter in N equals 2. After 2P, we have to move up to 3s. You can put 2 electrons in there as well. Now we've got 3 electrons left. After S comes P. We only have 3 electrons, and so we have to put those into there. So 3p3 is our last set. How many valence electrons do we have for phosphorus? 5, which also corresponds to its group number or its column number if we're just counting the main group. So skip the transition metals. And that matches with the 5 that we count up for our N equals 3. So in our highest energy level, highest principal quantum number of 3, 2 plus 3 gives us 5. So we did our electron configuration correctly. This is one way that we could check our electron configuration, or we could remind ourselves of the number of valence electrons. And then the number of core electrons is everything below that. And so that's going to be everything that's in here. So we've got 10 electrons, and these are core electrons. If we had done this with our shortcut, we look at the previous noble gas. What's the noble gas before phosphorus? Neon. We could also do a shortened version where we write Ne in brackets. Phosphorus has 15 electrons. Neon has how many? 10, because that's the number of protons that it has. So we'd use up 10 electrons, and we would have 5 electrons left. We're in row 3 with phosphorus, so we'd be starting with 3s. We'd put in our 2, which leaves us with 3 left. P comes after S, so 3p3. We would get basically the same electron configuration. We just get to skip a little bit with the neon. We would do the same 2 plus 3 for 5 valence electrons, and then the number of electrons that neon has is our number of core electrons. One of the ways that we can remember the filling order for our orbitals is with the periodic table. So this is by far the best way, in my opinion, to remember the order that we fill them up. It requires us to know that there are 4 blocks on the periodic table. So it can be divided into 4 blocks that represent the sublevels S, P, D, and F, so our different letters. Remember that the group number of a main group element is equal to the valence electrons. The row number of a main group element is equal to the highest principal quantum number for that element. So whatever row that we're in equals the highest n for the element. There are a couple of little weird bits here that I'll point out when we see them. Okay, so looking at our orbital blocks. Our orbital blocks are broken down so that our S block elements are in the far left 2 columns, our alkali and alkaline earth metals. So when we are in the S block, we are filling up the S orbitals. The S orbitals is whatever row that we're in. So for hydrogen, we're in row 1. We're in the S block, so it's 1s. We've got 1 electron, so it's 1s1. If we go down to like cesium, for example, we're in the S block, so it's S. It's row 6, so it's 6s with the first spot, so it's 6s1. So the number that goes in the upper right corner is just how many spots are you into that block. Our P block is all the way over in the right. So when we are in the P block, we're filling up our P orbitals. So our S is going to be full. We're past S. Now we're filling up for P. Boron is in the first position, so it's 2p1. Second row, P block, 2p. First position, 2p1. And then 2p2, 2p3, 2p4, 2p5, 2p6. So S is the far left, 2. P is the far right, 6. Our D block elements are in the middle. We'll do it correct colors. surprisingly visible. So our D block is in the middle. And if we look at our first row, what number do we see for our D? Can we read that number? It's 3D. But it's in row 4. So row 4, so we would expect it to be 4, but the first time that we see our D block show up is in n equals 3. So the number for the D block is row minus 1. This also applies for our F block, but for our F block, it's n minus 2, or row minus 2. We won't do any electron configurations for our F block, which is great news for us. Okay, so if we want to write an electron configuration from the periodic table, for this one we're doing it for chlorine. So chlorine, we have the previous noble gas is neon. So we take neon and we make it symbol inside of brackets. That represents everything up to neon. So we're going to start counting after neon. Let's circle it around the other way. So we're moving on to, what row are we in? We're in row 3. And what block is this? That's our S block. So we're 3S. Are we past the S block? Yes, we're past the S block. We're past the S block, so the S block is full. That means it's 1, 2, because there's 2 width. So 3S2, we're past the S block. We jump across our D block, because that shows up later. What row are we in? We're still in row 3. Row 3. So our number is 3, and what block are we in? We're in the P block. And what spot in the P block are we in? We're in the 1, 2, 3, 4, 5th spot, so 3P5. So it's row, block, how many spots into the block, or are you past it? If you're past it, you move to the next block. Okay, let me show you another one using bismuth as an example. Bismuth with the red outline. What's our previous noble gas for bismuth? Xe. Xenon goes in brackets. So xenon covers all of this, so we don't have to worry about any of that stuff. All that stuff is already covered for us. So we're picking up, we're starting off with cesium. That's where we start our counting. What row are we in? We're in row 6. And what block are we in? We're in the S block. So counting over, 1, 2, we're past it, right? So we're past it, that means it's full. There's 2 spots. So 6S, 1, 2, 6S2. What comes after our S block? I'm going to put D block. We're never going to use the F block, so it doesn't matter if we get it right. but I believe we would be filling in D. What's our weird thing that happens with D? It's row minus 1. So we're in row 6, D block, 6 minus 1. That means that this is 5D. Is bismuth past the D block? It is past the D block. So that means that this is going to be full. We are 1, 2, 3, 4, counting out the rows, the columns, sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You can always count it out if you're not sure, if you don't remember how many there are, but there's 10 for the D block. We also have the F block that shows up. What's our rule for the F block? Row minus 2. So it's 4F. The F block all fits in here. We're past it. It's 14 wide. You can count it out if you don't trust me. So 4F, 14. This is not really important. The order is not really important for us. After we get through all of that mess, what block do we arrive in? The P block. So we're filling up what number P? 6P. And we count spots that we're in. 1, 2, third spot, 6P, 3. Questions about anything other than the D or the F block? Okay, some for you to do with a periodic table included up here. You're welcome to use yours instead. Please write the electron configurations for these elements. So it looks like we mostly got it, or at least we've got it started. So for our electron configuration for each of the elements, first thing we need to do is find them. So chlorine, our previous noble gas is neon, so we can write Ne in brackets, and that counts for everything up until neon. And then we are going to start on row 3. The first thing that we hit in row 3 is the S block. We're 1, 2, we're past it. So we're past it, 3S2. We've filled up 1, 2 with our 3S. And then we jump across to aluminum, and aluminum is in our P block. Aluminum, silicon, phosphorus, sulfur, chlorine is our 5th spot. We're still in row 3, 3P, 5. For silicon, it's the same previous noble gas. We're also starting in row 3. We hit the S block first, so 3S. We're past the S block, so it's full. Jump across. We're in the row 3 P block, so 3P. And we're in the 1, 2 spot, the second position, so 3P, 2. For strontium, our previous noble gas is krypton. So Kr in brackets. And then starting off on the row that strontium is in, we're in row 5. And we are in the S block, so 5S. We're in the second spot, so 5S2. For oxygen, we can use the noble gas shortcut still. with helium. And then we're going to be 2s2, 2p4. We're in the fourth position of the p block in row 2. Questions about any of those? You might instead choose to count individually every single block, just jump element to element to count up these numbers. Or you might do it this way, or you might do some other thing. There are also some weird electron configurations. So because of sublevel splitting, because of SPD all being slightly different energy levels, the 4s sublevel is lower in energy than 3d. That's why 4s shows up before 3d on our periodic table. And because of that, the 4s energy level fills before 3d, but the energy difference is not very big. So 4s and 3d are close in energy, and because of that, some weird things can happen. So some transition metals have irregular electron configurations, and these are some of those weird ones. So what we would expect for chromium, copper, molybdenum, ruthenium, palladium versus what's found experimentally. And with the exception, nope, not that. With the exception of ruthenium, I accidentally swiped to a different app, the App Store. Because of the, other than ruthenium, notice that these all are 4, 9, or palladium's also weird. Ignore those. What we expect is 4s2, 3d4. What we see is 4s1, 3d5. And this makes a little more sense if we look at it as an orbital diagram. So this is what we would expect for chromium. But what we find instead is this. Let's do it in red so it's different. So rather than having four parallel electrons so close to having that half full shell, instead of that, it yoinks one of these electrons from 4s to get all 5, all with parallel upspin. Basically the resonance, them all being upspin, stabilizes it because they're all matched up, they're all in sync. It's a similar thing that happens for copper, and molybdenum, ruthenium, and palladium are weird. So I wouldn't expect you to remember those. In the case of copper, instead of half full, it's a full 3D subshell. The reason for that is that full and half full D shells are more stable. So you might get one of these, probably not, might show up on an exam. Questions? Okay, on to lecture 2 in the lab.